Hey everyone, welcome to the lecture for 3.7 on inverse functions. So we want our goals today to be verifying inverse function, determining domain and range of inverse functions, and being able to restrict the domain of a function in order to make it injective and graph its inverse. So an inverse function, I always think of it as the undo. So f does something to an input, right? So let's say I give you that f doubles your input. So if you give me 1, I produce 2. If you give me 4, I'll produce 8, right? So I'm the function and I double the input. The inverse of that is the undo. So how do we undo doubling? Well, we would divide by 2 or take a half. So if you give me 4, then I would split it in half and produce or output 2. If you gave me 2, I would cut it in half and I would spit out 1. So it's the undo of the original function. It's really important to note. So I know I touched on this last time. F of g of x, which was f composed with g. This is not multiplication, right? This is not f of x times g of x. We have other notation for that. It's not 3 numbers multiplied together, f times g times x. F and g are functions. That's a totally different beast. X is a number. So we have to be really mindful of what all this notation means. So similarly, f inverse of x is not equal to 1 over f of x. If you wanted to take the reciprocal of f of x, you would wrap the whole thing in parentheses, then apply the -1. This would be equal to 1 over f of x. Now, why is this so nuanced? Well, let's think about it. F, if we're applying this -1 symbol to f, as we are here, remember that f is not a number. It is a rule. It is a function. It's an action. It's like a verb. So it doesn't make sense to treat it like a number. So this notation here, when applied to a function, means the inverse function. However, if we were to wrap f in brackets, or rather if we were to wrap f of x in brackets as we are here, f applied to x for a specific x value, that actually produces a number, right? So an action on a number is going to produce another number. So then it makes sense in that case to take the reciprocal of that number. So let's say f of x spits out a 10. Well, it makes sense to say 1 over 10. It makes sense to do that. F by itself is just kind of an action or a verb. So until it produces a number for you, it doesn't make sense to take the reciprocal. So this is really important. So as I was saying before, F is an action. So in this case, in example 1, it's saying that f of 2 equals 4. So that means 2, if you plug it into the f machine, whatever f is doing, it spits out a 4. And similarly, if we were to plug in 5 into our f machine, whatever it does, it's going to spit out 12. And so if we wanted to consider what f inverse does, then what we would see here is that if I were to plug in 4 into the f inverse machine, it undoes what f does. So if f sent 2 to 4, then f undoes that. So it's going to take 4 and send it right back to 2. Similarly, if I plugged in 12 into the f inverse machine, it would spit out 5. It's the undo. Another way of thinking about this is in terms of are ovals, right? So we know that 2 and 5 through F, 2 got sent to 4, and 5 got sent to 12, right? So F is bringing, here's the domain of F, by the way, and here's the range of F. 2 got sent to 4. So that means if I was doing F inverse, I would just go back the other way. So this is F inverse. So F inverse takes 4 and it sends it to 2. It takes 12 and it sends it to 5. And so notice that in this case, the domain of F inverse is on the right and the range of F inverse is on the left. And we can see that for F and F inverse, we had this kind of crisscross matchup with domain and range. So the domain of F we see here is the range of F inverse, and the range of F is the domain of F inverse. And we'll see that coming up in a little bit in this video. So if we want to determine whether or not a function is actually an inverse of another function, we're going to rely on function composition. So what we're saying here is that if F and G actually, let me put it to you this way. If F has an inverse, then first of all, the inverse of F is going to be unique. You're not going to have multiple inverses. But here, what we're going to focus on is that if F has an inverse, which we're calling F inverse, then F composed with F inverse with input X equals X, right? So, and you also have to show this other thing too, which is that F inverse composed with F of X equals X, because we know in general, so the takeaway here is that in general, F composed with G is not equal to G composed with F. So we have to show both orders of composition in order to verify that a function and its inverse are actually true function inverse pairs. So let's look at an example here. So if f of x equals 1 over x plus 2 and g of x equals 1 over x minus 2, then is g equal to f inverse? So what you want to do is you want to compose f with g, and you want to know, does this equal x? And you're also going to have to show or ask yourself, is g composed with f of x equal to x? So these are both the things that you're going to have to investigate. So let's go ahead and investigate them now. So f of g of x, so this is going to be f of g of x is 1 over x minus 2. And what f does to its argument or its input is it takes, let's look at it like this perhaps. So now here's our input. And so what f does to its input is it does this, right? Whatever its input is, it's 1 over that input summed with 2. So that input is 1 over x minus 2. So now if we simplify the denominator here, we're going to get 1 over x. And this simplifies to x. So we have shown that f of g of x equals x. So this is true. So now let's go the other way. We're going to have g of f of x. So that was 1 over x plus 2. And this equals, well, what does g do to its input, right? So this is now the argument or the input for g. So what does g do to this? Well, g goes like this, 1 over whatever its input or argument is. And then from that, it's going to subtract 2. Well, its input is 1 over x plus 2. So this is the same thing as x plus 2 minus 2, and that simplifies to x. And so that's also true. So then we would conclude that g is the inverse of f. You could also say that f is the inverse of g. All right, so let's do another example here. So we want to, again, check, does f of g of x equal x, question mark, and does g of f of x equal x, right? So we're going to investigate both of these things. So f of g of x, well, g of x is 1/3 x. And then what f does to its input is it just cubes it. So it's going to take its input and cube it. That's what f does to it. It just says, whatever you're giving me, I'm going to cube it. And we're giving it 1 over 1/3 x. So this is going to equal, we know we have the property here that a b to the n equals a to the n times b to the n. So we're using this property of exponents here to say that this is 1 over 3 cubed times x cubed, and this gives me 1 over 27 by x cubed. This is not equal to x. So once we've shown that one of these equalities fails, now we can go ahead and conclude that g is not the inverse of f. If you wanted to just work on composition, you're more than welcome to figure out what g of f of x is. However, once one of the equalities doesn't hold, you're done and you just say, hey, it's not the inverse, and then you move on to the next thing. All right, so let's try one more example, and let's think about in advance whether or not we think that that g is the inverse of f, right? So what does f do? So let's look at this. So f, the first thing it does is it takes x, then it subtracts 1, and then it cubes it, right? Let's say cube it. G of x says the first thing you want to do is cube root it. Then you want to add 1. So let's think of it from this direction. F of x, it takes x. Actually, you know what? I need to scoot this over. So when you're undoing something, you want to think about, I always think about this, like think about how you get dressed in the morning. You know, the first thing you're going to put on is probably like your undershirt and like your kind of inner layers, then you're going to put on your outer layers, and then you're going to, maybe the last thing you do, let's say on a cold day, is you would probably put on your coat and your hat before you leave the house, right? So you have this idea of how you build up your outfit for the day. Well, when you come home and you've got your shoes on, you've got your hat on, and you've got your jacket on, right? Those big outer layers, you can't take off your socks until you take off your shoes, right? So when you're undoing something, you start on the outside and you undo it working in. And so that's kind of what I'm thinking of here is if I have X, I'm building up my inner layer. I'm subtracting one first, and then my next layer is cubing it. So if I want to undo that, I have to start with undoing the cube. Well, undoing a cube is taking the cube root. And then once I've taken off that layer, once I've taken off my jacket, now I can maybe unbutton my cardigan or whatever. And so that's going to be undoing that next layer. So if subtracting one was my inner layer, the undoing of that would be adding one, right? So I've got this idea of I'm going in reverse order and I'm undoing each step. That's the idea of an inverse. So we suspect then that the answer to this question is G equal to F inverse. We expect that the answer is going to be yes. So let's go ahead and show that it's true, or perhaps prove ourselves wrong. Maybe there's something that we hadn't thought of. So we want to check is f of g of x equal to x, and we also want to check is g of f of x equal to x, right? And we don't know for sure yet, but we've got a good idea. F of g of x is f of, well, g of x is the cube root of x plus 1. And then what does f do to its input? So whatever its input is, f is going to first subtract 1, and then it will cube it. So it's going to be whatever my input is cube root of x plus 1. So it subtracts 1, and then it's going to cube that. So let's simplify. I'm going to get the cube root of x cubed. Well, if I cube a cube root, I've really done nothing at all. So this is just equal to x. So we're halfway there. Now let's do g of f of x. So g of, now what is f of x? It is x minus 1 cubed. So what does g do to its input, to its argument? Well, g takes the cube root of it, and then it adds 1. So this is going to be the cube root of the argument or input being x minus 1 cubed. So I cube root that, and then I'm going to add 1. And so the cube root and the cube are going to cancel. I'm left with x minus 1 plus 1, and I get x. So as we initially thought, g is the inverse of f. So next, let's move on to finding domain and range. So we talked a little bit before we had this structure, this diagram earlier in today's video, when we saw how the domain of f was equal to the range of f inverse, and that the range of f was equal to the domain of f inverse. And that's hopefully very straightforward. There are times when this is going to be require some modification. And so we kind of have to be prepared to modify the domain of f so that f inverse exists as a function, right? So what do I mean by that? Well, I might be jumping the gun a little bit here. Actually, no, I'm not. Okay, So I'm going to kind of take this idea, be prepared to modify the domain of f so that f inverse exists as a function. And you might be thinking like, what is she talking about? So I'm going to show you real quick. So we know that the range of f is the domain of the inverse, and the domain of f is the range of the inverse. Got that. So let's look at some toolkit functions. We don't have to do all of them, but we'll do some. In particular, I want to look at maybe we'll just kind of limit ourselves to these ones. Cubed, squared, abs val, constant. 1 over x is good as well. Okay. So I want to start with the cubic. So a cubic function looks like this. And so we can see that the range, let me call this f of x actually, just for notation. So f of x is going to equal x cubed, right? So we've got domain of f. This equals all real numbers, right? Or you could say negative infinity to infinity. And the range of f is all real numbers, which again, negative infinity to infinity. And moreover, we don't have a repeat of any y values. And what that means is that f is injective, right? That was our other word for one-to-one. So what we have here is that without really any issue, right? There's not going to be any problem just simply swapping the x and y. So we're going to have that the domain of x equals the range of f inverse, and that the range of f equals the domain of f inverse, and all of these are the set negative infinity to positive infinity, or you could say all real numbers. Okay, so that one was pretty easy. So now let's think about absolute value. Here we have f of x equaling the absolute value of x. And we can see that the domain is all real numbers. But the range is from 0 to infinity, right? Because there's no negative values here. Now for f inverse, here's something that's going to happen. So consider this. I'm going to draw our little oval situation here, and I'm just going to give a few examples of what's going on. So on the top, we're going to have, let's say that this is f. And then on the bottom, I want us to consider what's going to happen with f inverse. So here we're going to have the domain of f. And here we're going to have the range of f. And on the bottom, we're going to have the domain of f inverse. And here we're going to have the range of f inverse. So of course there are infinitely many values, right? So let's just consider a few. So 1 and -1, 2 and -2, 3 and -3. So these are going to map to 1, 2, and 3. So we see that 1 and -1, they both map to 1. 2 and -2, they both map to 2. Similarly, 3 and -3, they both map to 3. So looking at this from left to right in terms of F, bringing the 1 and the -1 over to 1, bringing the 2 and -2 over to 2, etc., that's all fine and well. What we see here is that before considering F inverse, if we're just considering F, it's a function. So F is a function, right? Because each input goes to only one output. Like, for example, remember that if I had something like this, if -1 went to both 1 and 2, that's not a function. That was the no-no restricted thing that we couldn't do. But we do have this issue that F is not injective. Right? We have different X values going to the same Y value. Right? We had this idea of the vertical line test. So let's say this was 1 and -1, and this was 1. So both 1 and -1 both get mapped to 1, right? So this is this issue that we're having. And it's an issue because if I'm F inverse, I would just like to simply say, all right, just go back to where you came from. Well, I can't really do that because now what's happening is I have, for F inverse, remember it's going this way. So going from my domain to my range of F inverse, when I take one element and map it or send it to two different outputs, that is not a function. I can't do that. So the way I'm going to fix this the way that I fix this is I actually am just going to kill off some of the original domain elements from F. So let's consider the following. What if I just make this little adjustment? So let's copy this. And we'll paste it over here. Or not. And so now the idea is that I can fix this. I can fix this by doing the following. What if I just kill off some things in my domain? What if I just say no thank you to the negative numbers? I'll just literally whiting you out. So if I just got rid of these problem areas over here, I'm actually in really good shape. I'm no longer having this issue where for F inverse, I'm sending one input to multiple outputs. I'm saying, you know what, just go back to the positive version that you came from. So now all of a sudden we see here with the restricted domain, well, first of all, we're making F injective. So that F inverse exists as a function. Right? So we've kind of cleared up this issue. So how does that look graphically? Well, we see how we have these repeat Y values. What if we just did this? What if we're just like, you know, I'm not super into that part over there. So now all of a sudden, I don't have this vertical line issue. It's gone. I've removed it intentionally and very specifically. So now what I want to do is I want to restrict my domain. So consider f of x equals the absolute value of x just on 0 to infinity, right? So now I'm just looking over here. I've restricted my domain. I'm like, negative x values, get out of here. You're really ruining my ability to have an inverse function. So I've restricted my domain, right? So this is, so now I have the domain of f equals 0 to infinity. I still have that the range of f, it's still the same as it was before, 0 to infinity. And I also have that the domain of f inverse, right, is going to be the range of f, which is 0 to infinity. And I also have the range of f inverse is equal to the domain of f, which was 0 to infinity, right? So by uninviting some of our problem children to the party, I've accomplished what I wanted to, which was having it so that f inverse exists as a function, meaning that I've made f invertible, and that I have this nice matchup between domain and range for the function and inverse pairs. So the trick to doing that is just make f injective. Once f is injective, you can just flip-flop, crisscross all day. If you don't have that f is injective, you've got to do a little work on the front end. So this is going to be the exact same thing that happens with x squared. Okay, so we did that one. So f of x equaling x squared, it's the same story as what's happening here, right? And so I'll kind of leave that to the reader. In the case of 1 over x, so that looks like this. So we have here that f is injective. So we know that the domain of f I can plug in anything but 0. So it's going to be negative infinity to 0, union 0 to negative infinity. And the range of f is the same. So we can see that the height achieves any value except for 0. So the domain and the range are actually the same. And because f is injective, I can almost just like blindly go into this problem and say that the domain of f is the range of f inverse. And that the range of f is the domain of f inverse. Which is really nice. So again, the only issue that arises is when f is not injective. When f is injective, I can just kind of very cavalierly apply this concept. All right, so next we want to find and evaluate inverse functions. So here we have a table. And again, when we are finding an inverse function, we always have to begin with asking ourselves, is f injective? Is f a one-to-one function? Injective and one-to-one, those mean the same things. So notice how this statement says once we have a one-to-one function, right? So that's always the first step, making it one-to-one, making it injective. So once we do that, we can evaluate its inverse at specific inputs and kind of make a table or come up with the function or come up with the graph, whatever. So in this case, for example 5, we have a function f with input t, and they're asking us to find and interpret f inverse of 70. So this function is showing distance in miles that a car has traveled in t minutes. So like, for example, just reading off the table, in 30 minutes, the car has traveled 20 miles. Right? In 50 minutes, the car has traveled 40 miles. It's not great. Etc., right? So that's how we're reading this table. There's a context here. Now, in order to find f inverse of 70, so if f of 90 equals 70, right? We have that here. Then what this means is that f inverse 70 equals 90, right? You're just flip-flopping them. What if I said this too? What if I said f of x equals, let's say I said f of x equals 60, and I said find x. What would you do? You would go to your table and you would look at your output and you'd be like, okay, I see 60. What is the x value that's corresponding to that? Oh, it's 70. Okay, so x equals 70. Right, that's how you would do that problem. What if I asked you to find f inverse of 60? Well, you would go over to your table and you would look at, okay, where is the output 60? And what was the input that I used to get there? Oh, it was 70? Well, guess what? Those are the exact same problem, right? This is the same concept here. So if your notation is kind of driving you crazy, first of all, I assure you, you will get used to it over time with enough practice. But you can always try to reframe the problem into something that makes more sense to you. So the next part of this example is find, check, found, and interpret f inverse of 70. So f inverse of 70 we saw was 90. So again, 70 was the miles driven, and 90 was the time in minutes. So really what we're asking is, how long did it take to drive 70 miles? And the answer was 90, right? So that's the interpretation of this. Whereas saying f of 90, that's saying how far will you drive in 90 minutes? You will drive 70 miles. All right, so now let's say we have a graph of a function rather than a table. So a function g is given here in figure 5. Find g of 3 and find g inverse of 3. So g of 3, what does this mean? It says, where did g send the x value 3, right? So I look at my x value 3 and I see, okay, where did g plot that? Okay, this is the point 3, comma, g of 3. The height is g of 3. Well, so we see that g of 3 equals 1, right? You're just going over to your x values, your input, and your height. Why do you think we write y equals g of x, right? It's because g of x, the output, is plotted on the y-axis. G of x, the output of x, is plotted as the height. So the height when x is 3 is equal to 1. All right. Now it's asking us to find G inverse of 3. So this is really asking, where did the height y equals 3 come from? You might say, what x value got sent to 3? All right, so let's look at that. When the height is 3, what was the x value that corresponds with that? It was 5. 5 got sent to height 3. So what we have here is that G inverse of 3 is equal to 5. So this is the point 5 comma G of 5. Right, so we see here that G of 5 equals 3, therefore G of 5 equals 3, so G inverse of 3 equals 5. That's the pair, flip-flop. All right, so probably the most fun, well, the second most fun thing to do is to find an inverse represented by a function, a formula. So first, you always want to make sure that f is 1 to 1. Can't say this enough. I do it a little bit differently. I usually switch x and y, and then I solve for y. So the other option is you check that it's 1 to 1 or injective. I switch x and y, and then I solve for y. This is the exact same thing. They'll get you to the same place. Okay, and then you're looking at it, example 7, you're like, there's no x and y. It doesn't matter. Just whatever your two variables are. If it's x and y, swap them, solve for the other one. If it's c and f, swap them, solve for the other one, right? So this is a formula that gives Fahrenheit temperatures as a function of Celsius. So your input is Fahrenheit. Your output is Celsius, right? So this is a linear function. It's a line, right? It looks like this. Whatever. So I don't know. It's clearly not having any of these vertical line test issues, right? I'm not having any of these problems. So this is injective. It's a linear function. It's injective. There's only one linear function that's not injective if you consider the constant function to be a linear function, which I could see an argument for either case. That one is not injective, but anything with a non-zero slope, you're good to go. So what we're going to do, it's injective. So now I'm going to switch F and C, right? So this is switching F and C. So this was step 1. This was step 2. For me, and the way I do it, I switched my input output. And now I'm going to go ahead and solve this for C. So what I'll get here is F equals 5/9 times C minus 5/9 times 32. Or actually, I'm not going to do that. I'm going to do something a lot smarter. I'm going to multiply each side by 9/5. So I'm going to get 9/5 F equals C minus 32, and then I'm going to add 32 to each side. So I get 9/5 Fahrenheit plus 32 equals C. Right, and so in this way, we've computed the inverse function, right? So this is actually, maybe let's think about it this way. What if we had c of f, right? A function that depends on its input f equals 5/9 f minus 32. Then c inverse of f would be 9/5 f plus 32. This is kind of a wonky example, which I won't get into why I feel that way, but let's do another, let's do example 8. All right, let's find the inverse of the function f of x equals 2/x minus 3 plus 4. So the first thing I'm going to do is I'm going to say, is this injective? And what I'm going to do for that is I'm going to look at a graph. So let's rely on our function transformations, right? So we know that we have the toolkit function 1/x, right? And the first thing I see, okay, and it's 2, so it's got a compression, whatever. The first thing I see is that I've got a horizontal shift to the right by 3. So now I'm going to have something like this. And then the next thing I see is that I've got a vertical shift by 4. So now I'm going to be like this. But no matter how I cut it, I'm still not going to have this repeating y value thing. Like I'm not going to have an issue. So yes, it is injective. Next, I'm going to switch x and y. So originally I have y equals 2/x minus 3 plus 4. And I'm going to switch x and y. So I'm going to have x equals 2/y minus 3 plus 4. So this was my step 2 where I switched my input and my output. And now I'm going to go ahead and solve for y. So in step 3, I'm going to solve for y. So x equaling 2/y minus 3 plus 4. I'm going to go ahead and subtract 4 from each side. So x minus 4 equals 2/y minus 3. I'm going to do this. What will I do? I'm going to multiply each side by y minus 3. So I've got y minus 3 equals, sorry, times x minus 4 equals 2. And I'm now going to divide by x minus 4. So I get y minus 3 equals 2/x minus 4. And then I'm going to add 3. So I get that y equals 2/x minus 4 plus 3. So this is f inverse. So we say that f inverse of x equals 2/x minus 4 plus 3. You can always verify that what you got is the inverse, right? So let's say I was on taking a test maybe, or working on an engineering problem at a company I'm at. And I really wanted to double check that these two are the correct inverse function pairs. Well, I would just check. I would check, is f of f inverse of x, does it equal x, right? Well, f of f inverse was 2/x minus 4 plus 3. And what if you take your time? It's really not that bad. So f, what it does to its input is it says, okay, 2 over my input minus 3, right? And then plus 4. That's what f does as a function. It takes its input, subtracts 3, inverts it, multiplies it by 2, adds 4. So I have 2/x minus 4 plus 3. But we can see just straight off the bat that something really nice happens. So this plus 3 in blue and then the minus 3 from F, those are going to cancel. So I get 2 over x minus 4 plus 4. And then I'm just going to flip this. So this is 2 times x minus 4 over 2 plus 4. These 2's cancel. I get x minus 4 plus 4. I get x, right? So, and you could do the same for f inverse of f of x as well. So again, not that the problem asked us to do this, but it's always good to check your work. So remember that f inverse is going to take f as its input. So this is going to be f inverse of f of x. So f of x is 2 over x minus 3 plus 4. So now this is the input for f inverse. Sorry, I switched up my 3 and my 4. 2 over x minus 4 plus 3. So now this is the input. So first I want to write down what f of x is. It's 2 over x minus 3 plus 4, right? That's f. That's what's going into f inverse. So now we have to ask ourselves, well, what does f inverse do to a function? Well, what f inverse does to a function, to its input, is it is going to subtract 4. It's going to flip it, multiply it by 2, and then add 3. What am I really saying? 2 over whatever its input is. Subtract 4 in the denominator, and then on the outside, we're going to add 3. So my input is 2 over x minus 3 plus 4. And so here we can see that as soon as we can kind of get our brains right and for our input and the composition, everything shakes out pretty smoothly thereafter. So in the denominator, those 4's are going to cancel. Keep change flip. So I'm going to have 2 by x minus 3 over 2. Those 2's cancel. X minus 3 plus 3, and I get x. So yeah, so here we're just verifying that it is, in fact, an inverse. All right, in example 9, we're going to find the inverse of the function f of x equals 2 plus x minus the square root of x minus 4. So remember that we have to be mindful of the domain. So let's just kind of work this as we normally would. So 1, is f injective? F is injective. Its graph looks like this. So remember, we have our toolkit function, square root of x, right? Well, this guy tells me I'm shifting to the right by 4. This guy tells me I'm going up by 2. But regardless of these horizontal and vertical shifts, I'm still 1-to-1. I pass the vertical line test at every point. So I'm sorry, the horizontal line test at any height. So it's injective. So this was our f of x, right? Okay. So I've determined it's injective, and the next thing I do is I switch x and y. So I have y equals 2 plus the square root of x minus 4. And I switch that to x equals 2 plus square root of y minus 4. And now I'm going to solve for y. So I have x equals 2 plus root y minus 4. So in order to get this y free from the radical, I've got to make sure that the radical is the only thing on the side of the equation. So I'm going to do x minus 2 first, and then now I have y minus 4. So now I'm ready to square. So I'll have x minus 2 squared, y minus 4 squared. So I'll have x squared minus 4x plus 4 equals y minus 4. This is actually technically the absolute value of y minus 4. I think I'm going to glance over that right now. So now I have x squared minus 4x plus 8. And this equals y. But we have to be a little bit careful because remember that the domain, so looking at our function here, the domain of f is from 4 to infinity. And the range of f is from 2, right? So when x is 4, it's the square root of 0, and then I add 2, so this is 2. So the range is from 2 to infinity. So how does that play out here? Let's factor this really quickly. So this is, what would this be? What would we get? How could we do this? Right, so here we're going to have f inverse of x equals x squared minus 4x plus 8, but we have to restrict our domain because f inverse itself is not a one-to-one function, right? This is a parabola. So we've got to take the domain of f inverse as the range of f. So we just got to keep it from 2 to 8. And then we have to take the range of f inverse as the domain of f, which was from 4 to infinity. All right, so I think for me, the most fun part about inverse functions is just using graphs to figure out what the inverse is and what it does. So the cool thing is we're just going to use the idea of reflection, not across an axis, but across a certain line. And that line is going to be y equals x. So just really quickly, let's go back to our example we just did. Our second step is always switching y and x, switching our x and y coordinate. So when y equals x, right, that's that swap. You should relate it in your mind to that swap, y equaling x, and switching them out. And that is actually our line of reflection. So for example, here, blue was our original. Here's the line y equals x in orange. And if I reflect it about that line, this new teal graph here becomes our inverse function. So let's say here that that f of x equals x squared. And we're restricting it on the domain from 0 to infinity, right? Because we know that x squared is not injective. But once we restrict the domain to make f injective, now it's invertible. Well, how do I undo squaring something? I square root it. Right, so that's exactly what's going on here. All right, so let's go ahead and apply that method to this function. So this function, they didn't give us a formula, and that's fine. All I'm going to do is I'm just going to graph the line y equals x. And I'm just going to reflect this across that line. So that means that this point becomes this point, right? I'm reflecting it across this line, switching my x and y, right? So if this is the point 1, 0, if I switch x and y, well, guess what? That becomes the point 0, 1. All right, what about this point here? Well, that point becomes this point because here I have 2, 1. If I switch x and y, guess what? That becomes 1, 2. All right, and then how about this point down here? I've got, let's say this is -3 or 0, -3. That's going to go over here. So if this is 0, -3, then this has to be -3, 0. I'm just switching those x and y values. And I can do this all day long. So then when I graph my function, I'm just going to, let's see, this point would be from this point over here. Right, so now, if I did that correctly, this is f inverse of x. And this was the original f of x. All right, so let's practice that one more time. Here we've got, we already know what this is. We've seen this before. This is actually f of x. It is the, it's the radical, right? But it's shifted over to the right by 2. And it looks like it has no compression. So this should be the square root of x minus 2, right? So if I plug in 6, I'm going to get 6 minus 2 is 4, square root of 4 is 2, so I'm all set. Not that you have to figure out what the formula is. I'm just saying to maybe give you some familiarity with what you're looking at. And it never hurts to practice writing your formula for transformations. So I'm going to graph the line y equals x. And then I'm just going to flip these. So, right, I've got 2, 0 goes to 0, 2. 6, 2 goes to 2, 6. Right? 8, so let's call it 2.5, goes to, let's say, 2.5, 8. So let's play something like right here. And just for fun, we could figure out what this formula is, right? We've seen how to do that, switching our x and our y. I believe that. All right. This line is supposed to go through that point, so I'll just make the point bigger. So that was sketching the graph of f inverse, and we want to find f of 6 here in 30. So we see here that f of 6 equals 2. And then it says find f inverse of 2. Well, f inverse of 2, just where did 2 come from? Well, came from 6. But, right, that was the old way of doing it. But we could look at the orange graph. If I plugged in 2, guess what? It's that big blob of 6. So I could look at it either way.